It was a great privilege to present the petroleum resources of the Great American Carbonate Bank to the North American group of the HGS on April 25, 2011. HGS asked me to record this presentation so that future explorers could study and become more familiar with the material. This paper came about as an APG memoir on the Great American Carbonate Bank as a tribute to the great carbonate geologist James Lee Wilson. And I was very fortunate to be asked to write the petroleum chapter. This memoir is due out in 2012, and you can see James Lee Wilson is on the right of the screen. The main part of this talk, the importance thing to remember about this talk is that we have 100 years of exploration history for the Great American Carbonate Bank, and the purpose is to take these insights and lessons for the explorers of today so that they can use them going forward for future exploration. And I knew to do this chapter we had to have good up-to-date production information, and IHS obliged us by sharing their vast production databases. Most of the production is in the Midcontinent, but it's clear that the Great American Carbonate Bank is a continental-wide carbonate bank that extends into Canada and Greenland. One of the main things about the reservoirs in the Great American Carbonate Bank is that they are part of a larger petroleum system with source rocks and seal in strata that are not of the Great American Carbonate Bank, but that are juxtaposed by faults and impinged upon by onlapping of the unconformity and various configurations. So it's very critical to understand much more than the carbonate bank to understand the petroleum system. The early workers on unconformities, particularly Leverson and Sloss, noted that unconformities had profound impacts on hydrocarbons. And I would like to coin the phrase unconformity thinking here to acknowledge this importance, because it's very clear that the predominant oil and gas production out of the Cambrian-Ordovician reservoirs, the majority of the production is associated with the unconformity. And the early workers in Leverson's 1943 paper recognized clastic systems had inherent porosity changes at unconformities, that there were pressure differentials that could attract and affect the way hydrocarbons migrated, and that old traps or paleogeomorphic traps had the opportunity to get many charge pathways and therefore a favored situation. But these were basically observations about siliclastic carbonate systems. And the Great American Carbonate Bank is a carbonate that is greatly dissolved and karstified and fractured by this unconformity. So when we're talking about the Great American Carbonate Bank unconformity, the carbonates add an entire new dimension. This shows the middle portion of the carbonate bank that is with the dolomite pattern and the limestone pattern where the majority of production occurs, and the explorer today will recognize the reservoir names, the Ellenberger, the Arbuckle, the Knox, the Prairie du Chien, and the Beekmantown. So when we say Great American Carbonate Bank, we are referring to all of these very common oil and gas reservoir names. This strat chart by Bill Morgan, one of the co-editors of the volumes, very nicely shows that the unconformity is a major hiatus at around the 472 million year boundary, and that the rocks that we're going to be referring to vary from 472 million to 488 million as the lower Ordovician, and that the upper and middle Cambrian component of this includes rocks as old as 513 million years. And this chart is an amazing accomplishment by Bill Morgan, because what it does is it compiles the stratigraphic units all across North America and gives the cycles and the age equivalencies. The volume that's in preparation has about 30 chapters on local areas, and you can see how far-ranging these chapters are. The big picture, as I like to call it, is we can see in the middle of the midcontinent of North America what I call the breadbasket by the light blue area, but it's clear that the extent of the carbonate bank goes far into Canada and also into Greenland. This zoom in of the midcontinent of the U.S. highlights the oil and gas production, with red and yellow colors being fields that are the richest, and notably they occur in the Permian Basin and in the central Kansas uplift, but also there's quite a bit of green, which represents green and yellow that represent production in Kansas, Oklahoma, and up into the Appalachians, Ohio, and Michigan. Reviewing the production, there's about 3,650 fields that produce oil and gas from Cambrian Ordovician reservoirs, and 4.1 billion barrels is oil and 21 TCF is gas, and it includes some gas giant fields. Taken together in barrels oil equivalency, this is about 7.7 billion barrels, so it's clear that this is a very significant stratigraphic unit. And since the majority of the oil and gas equivalent is oil, 57%, it's timely to revisit these under current scenarios of high oil prices. As we look at the 30 basins that produce from the Cambrian Ordovician, or the Great American Carbonate Bank reservoirs, it's clear on the far left the two basins dominate, the Permian Basin and the central Kansas uplift, where Permian Basin has 5 billion barrels equivalent production, and central Kansas uplift has 2 billion barrels. So these are clearly the dominant players. There's about a dozen fields that have 10 to 100 million barrels of production, and on the far right there are a handful of fields that have lesser amounts of production, and if you're an optimist, as I am, these are potentially underexplored areas. And looking at the basins by the number of fields, once again, the central Kansas uplift, Permian Basin dominate on the left, and I call your attention to several areas on the right that have a very few fields, and once again I would offer that they may be possibly underexplored areas. This is a diagram that shows all of the fields represented by a black line. It is by percentile. So, for example, of the straight average of the 7.7 billion barrels, 3,650 fields is about 2.1 million barrels of field. But the reality is that there are some very large giants that dominate the production, and there are very many small fields. So the average, straight average, does not work well in understanding these fields in aggregate, or as we look at any one of the individual basins, which are shown here by the various colored lines. Just to get a global view of the reservoir that affects the production, the cyan in the middle of the continent represents dolomite, and as we go to A, that's a very up-dip reservoir position, so there's a lot of interbedded sandstones and dolomites, and as we work down through the midcontinent, the reservoirs are almost entirely dolomite. In the distal portions of the production, as we get to the south, they become more limestone rich, and as we go off ramp they become more distal. So we'll look at a composite section, if you will, from A up dip to C prime down dip, and these are three separate sections that are put together. The red line represents the Knox unconformity, and that is a stratigraphic reference point, and we can see that the dolomite is cyan, and the interbeds of sandstone and dolomite occur in an up-dip position. That is important in basins like the Michigan Basin, where the Prairie du Chien has interbedded sandstones and dolomites. And then as we move towards the central part of the production, there is mostly dolomite, and as we go into some of the allocogen settings like the Anadarko Basin, the Mississippi embayment, and also a more distal ramp setting, we pick up increasing more limestone. And in some of the positions we can see interbeds of dolomite in light blue and limestone in darker blue in a more outer ramp setting. And of course, all of these reservoirs that were deposited in various depositional patterns are affected by the unconformity, which has a duration of anywhere from a few 100,000 years to perhaps as much as 10 million years. And this unconformity at the top of these reservoirs, it dissolves them, causes caves that collapse. There's a lot of diagenesis and fractures associated with this major exposure surface. If we look at where oil and gas pays occur in the various depositional settings, this diagram helps illustrate that the interbedded sandstones and dolomites, as they play out in an up-dip scenario, can have multiple pays over, in this case, an example from the Michigan Basin, where there's 900 feet of sand and dolomite, and there are pays at the top. This would be where the unconformity is, but there are pays all the way down, and you can get stacked pays. If we look at the MID DIP shelf dolomite setting in the middle, which is where most of the production comes from in the Great American Carbonate Bank, it's clear that whether we're in unconformity traps like those in Kansas or in big structural blocks such as the Permian Basin, Oklahoma, that there are big dolomite reservoirs, but that the pay is basically in the top of the Arbuckle, Ellenberger, Knox, and that the limits of the pay is controlled by the column height. And then when we look in a down dip setting where perhaps it's in an allocogen like the Anadarko Basin or outer ramp where there are these red circles represent pay in a dolomite setting surrounded by limestone. When we look at the dolomite tongues in an overall limestone horizon, we can find pay. Their pay can occur in places like the Brown Zone in the Anadarko Basin, 900 feet from the Arbuckle unconformity, because the limestone at the top of the unconformity down to the Brown Zone dolomite is tight and is not productive. So it's usually very instructive to understand how hydrocarbons are trapped, to look at a variety of maps and cross sections over different fields to get kind of an experience for the wide variety and diversity of how fields work. And so what I thought we could do is we'd look at some examples. You can see the names here from the various regions, and we'd work from an up-dip position in Michigan, which happens to be the interbedded sandstones and dolomites with potential stacked pays. Look at some of the MidContinent fields that have large structures, and then we'll look at some of the examples as we go into a mixed dolomite limestone outer ramp setting. So in the Michigan example, this is a log that represents sandstone and dolomite, and the different circles represent pay zones, and it's clear that a 50 to 100 foot gas column pays not only at the top of the Arbuckle-Ellenberger, where the red line is, but it can pay well down into the section, and that is possible to get stacked pays over a large stratigraphic interval. And that's because, in this case, the reservoirs are sandstones, 4 to 12% porosity, and argillaceous dolomites are actually acting as the seals. And it was interesting, I found a reference in one of these papers that talked about the Arbuckle-Ellenberger as the potential to find pays deeper down rather than just drill at the very tops of the Arbuckle-Ellenberger. And I think this is very appropriate for this up-dip interdetrital belt setting. And I find this interesting that Bartram and his co-authors said this in 1949. As we look at some of the examples over in Ohio, there are some great paleogeomorphic traps because of the unconformity, and these show up as the Beekmantown and Rose Run are truncated by the unconformity. And very notably, there is a very rich shale source rock, Cambrian source rock, below the Great American Carbonate Bank up here. And since hydrocarbons have to be introduced to the carbonate reservoirs, normally that occurs by fault juxtaposition or onlap at the unconformity. This is an interesting example where beneath the carbonate bank there's a source rock basin of potential great interest. So something to think about as the possibility of offering some interesting charge scenarios. If we look at one of the detailed fields of South Canaan Pool in Ohio, you can see the topography created by the unconformity and the pinch-outs and the hydrocarbons trapped at that unconformity in paleogeomorphic traps. And in Kansas, the ability of the unconformity to erode erosional remnants is very dramatic, and even more important is the hydrocarbon fractionation of gas in down-dip fields and a mixture of gas and oil in the mid-dip fields and oil in up-dip fields. This is classic Gusso hydrocarbon segregation. Now, as we look at some of the large structural fields in the mid-continent out of dolomite reservoirs that are in big structural blocks, one of the very notable examples is the Oklahoma City field, which had an amazing IP from its initial well, and several of the wells have had extremely high rates, such as this one, over 6,500 barrels of oil a day from the Arbuckle at 6,400 feet. And that's one of the amazing things about the Great American Carbonate Bank reservoirs, is that because of the fractures, phenomenal wells can result. An example of another major structure that produces out of dolomite reservoirs is Keystone Field in the Central Basin platform of the Permian Basin. And you can see that there are several very large structural fields and companions to Keystone. One of the interesting fields and trends on the eastern shelf of the Midland Basin occurs because the unconformity, again shown in red here, produces karst within the Ellenberger and caves that collapse and fill with shale, and this would be the cave floor. And what's interesting is the cave filled that shale actually acts as a stratigraphic seat seal. So there's Suggs Field on the eastern shelf of the Midland Basin is basically an interesting stratigraphic trap produced from the karst fabric. And a particularly unusual but notable hydrocarbon accumulation is in Major County, Oklahoma, which is a astrobleem impact, and this produces from the Central Basin uplift and some of the crater rim in the Arbuckle dolomite. It's one of the more unusual trap types. Because the large structural blocks can have giant fields in them, it's worth taking a little bit of time to study them And I wanted to tell a story. I had an opportunity to work Wilburton Field for a major company in the early 90s. Wilburton, it was a 350 BCF field. It was recognized in the very late 80s, early 90s as being a significant discovery in the Arkoma Basin. And the first thing I did was I made a map on the up-thrown block and a map on the down-thrown block. I made a cross-section, and I tried to reconcile the gas water level in the field. And when I did, I had some very powerful observations that I want to share about the potential to predict the viability of trap when the carbonate bank is encased not entirely in shale or seal, but when it has sandstones that encase it that can potentially cause cross-fault leakage. And it's because of that that in situations like this, it's very important to make a fault plane map. So to zoom in on the Wilburton Field, it's in Latimer County, Oklahoma. Mapping the structural closure at the red horizon, which is the unconformity, the top of the Arbuckle, which is the base of the Simpson, the sandstones above it. It's very clear that there's a very large 14,700 acres of closure with 1,900 feet of relief mapped on this surface. However, when we look at the gas productive area, it's clear that only about 6,500 acres are gas productive within about 1,100 foot of column. So what happened between the 1,900 feet of structural closure and the 1,100 feet of gas column? There's about 800 feet less gas column than structural closure. Well, interestingly, that is the thickness in this area, 800 feet, of the Simpson sandstone. And in a cross-fault juxtaposition diagram, it's clear that the Simpson, although very tight, 2 to 3% porosity, not productive in its own right, it's not a seal. And so it's really a waste rock and it's a leak point. So in doing a critical fault map, it's clear that that is what controls the gas water level, is the highest elevation of the sealing lithology across the fault. So when we look at it in this dip cross-section, north-south, right here, it's clear that the gas column spills right at that critical point, and that is the very lowest elevation of the seal, and that's what's controlling it, and that this 800 feet is an effective seal across the fault. And so, knowing this, we can use several examples. Okay. Look at some seismic examples, and here is a very nice horse block on seismic. This is a typical prospect in the Arkoma Basin. Very complicated thrust sheets above in the allochthonous section, and this is the autochthonous section below the Pennsylvania thrust. And it's clear that there are horse block highs down here that look attractive for drilling and have been drilled. And so when one evaluates this particular prospect, it's clear that the cross-fault juxtaposition against the sands make this a non-sealing horse block. There are some examples where there's substantial amount of throw. Here is the Arbuckle in red and the Arbuckle in red here, and there's over 2,000 feet of fault throw, so clearly more than the 800 feet to overcome the Simpson. And I just point out that there is a thin Pennsylvanian sand called the Spiro. And the question is, would you drill this prospect? And the answer is, well, the company I was with did, because it's one of those cases of, would you drill this well again, knowing that it was a dry hole? And the answer is, I would drill it again. And the reason is, we did not know whether the Spiro was going to leak it off, and if we had too much throw. And it's entirely possible that the Spiro could have been faulted itself and that the system could have been backed up. But unfortunately, this does raise the issue that there is a very important window of fault throws when looking for Arbuckle blocks in sandy areas. And so I call it the Goldilocks of fault throws. In some basins, like the Arkoma, you need to have enough throw to overcome the leaky Simpson, but not too much throw in order to juxtapose spiral sandstone as a potential leak to the system. And so when we look at Wilburton, we can see that there are many dry holes shown in red drilled before Wilburton and many drilled after Wilburton. And I would say, as an explorer, by definition an optimist, that I believe there will be other Wilburtons found, but I can tell you that it will be important to use fault trap analysis in order to find them. One of the great explorers and inspirations to me is Captain James Cook. And Cook had a very important lesson for us, and that is he ventured off of the beaten path. And in the early days of Pacific exploration, he went into lightly explored areas, and not surprisingly, rather than tread the same paths that previous explorers tread, he found more islands than anybody else. And so I find that as a great example, because several of the examples of discoveries we'll talk about now occurred in the Cambrian Ordovician system far away from other Cambrian Ordovician production at their time of discovery. And I can't help but point out that in this portrait by Nathaniel Dance, he calls to attention something that I think a lot of us middle-aged explorers can relate to. Okay, Maben Field. This is an amazing field. It has about 51 BCF, or about 8.6 million barrels equivalent oil and gas. Maben Field is in Mississippi, right where the arrow is, and at its time of discovery, it was 590 miles from significant Cambrian Ordovician production. The nearest significant production was Wilburton, and that was over in the Arkoma Basin that we just talked about. Interestingly, there was a 1972 show well that Texaco drilled that had some gas shows and that continued to produce a small amount of gas for a very long time. And astute explorers came in and rediscovered this field in the 1990s. And what happened was, this Texaco well was making marginal rates of 100 to 200 MCF gas a day, largely forgotten by industry, but it was clear that it was not declining and that the pressures were not declining. And astute observations enabled a team, FINA and others, to realize that this was a larger tank that was not being drained by this well. And in the middle 1990s, FINA and others came in and were able to get some very substantial wells at 5 million cubic feet of gas a day, offsetting and up dip of the original Shealy well. And now this field has produced, as we say, about 60 BCF. So Maben Field is a great example of a comeback story. Now, one of the things, realizing the comments earlier about large structural blocks and the importance of crust fault seal, if we look at some of the major basins along the Ouachita Marathon thrust belt, like the Valverde, the Kerr, the Arkoma Basin where Wilburton is, the Black Warrior Basin where Maben Field is, and we look at the Carboniferous, there's a major source of Carboniferous sands coming in from the north and the east. So this is very, very sandy area in Mississippi and very sandy area in the Arkoma, but not so much so as we go towards the west. And interestingly, this cartoon represents, here's top Arbuckle, and here's a big fault structure, and here's top Arbuckle, same fault structure. You can see that in the Black Warrior Basin there were many sands and potential thief zones, so it's very difficult to get a trap. But Maben does work, and it does meet the criteria of very rigorous trapping in a sandy world. And similarly, in the Arkoma Basin, Wilburton Field, as we've talked about, it has to have just the right fault throw, not too much, not too little, and large fields result. But remember when we talked about the Permian Basin having the preponderance of the production, 5 BCF, and some very big gas giants, it's clear that the reason it does is because it's very distal to the Carboniferous sands and other potential leak zones that could be a trap risk. So the sealing configuration is very, very favorable, and the production is according. And using this model, some of my colleagues and I have explored for large structures in the Kerr Basin, because there it's a scenario where there's very favorable seal encasing the Ellenberger reservoirs. Let's look at a large field now in a more down dip position, Healdton Field, which is in a place where the brown zone, here's the top of the Arbuckle, this is the Knox unconformity, and this is one of the cases where there's limestone intervening down into the brown zone, which is a dolomite zone. And so here is a case where there is significant production on a structure that's far down 900 feet, 500 to 900 feet from the unconformity. And this is what happens in some of the outer ramp settings and also going into some of the allocogens. And these are two slides given me by Rick Fritz, and Rick makes the point that as we get into some of the more subtidal portions of the reservoirs, as we go into more outer ramp settings, that there are some better reservoirs potentially in the oolitic and the subtidal grainstone facies, and that it's clear that some of the better reservoir can occur in some of these subtidal facies. And then to go in a really down dip sense, I'd like to share with you what is in effect an unconventional play for the Cambrian Ordovician. It's not in the carbonates, but it's in the Cambrian shales of the Conasauga Shale, which has source potential. And Bill Thomas has written several papers on this. In the Appalachian Belt, there are these ductile thickened zones, and he calls them mushwads, which is a term referring to malleable unctuous shale with weak layer accretion in a ductile complex. And so these triangle zones of source rock-rich Cambrian shale can be intensely deformed and fractured, and there are some who suggest that this might be an unconventional play for the future. I have to tell you a story. I want to go back now. Let's leave the unconventional thought about shale, and let's come back to the main topic of this paper, of this presentation, which is the carbonate reservoirs, and in particular the karsted dolomite reservoirs, which represent, I would say, about 80 to 90% of the production for the Great American Carbonate Bank. And the fact that the karst alters the carbonates can make for some very big surprises. And if you talk to people who have explored for the Arbuckle, Ellenberger, Knox, they almost always have stories about bit drops and surprises, and it can be extremely, extremely exciting. So I had, as I was evaluating for Shell, the Wilburton Field back in the early 90s, I had a log and I was trying to make sense out of it. And I went to see a colleague, not Gus Archie, but a colleague of Gus Archie, Bert Tumier, who had developed Archie's equation with Archie and was one of the classically trained petrophysicists. I brought the log of one of the wells in Wilburton Field, and I asked him to help me understand what was going on. And so he looked at the log. Bert said, this is really something. He said, this is terrible. He said, this is the worst rock I've ever seen. It's like 2 to 4% porosity. He says, young man, why are you wasting my time asking me to to evaluate this. And I said, well, Bert, it's this particular well has already produced 43 BCF. And I remember shortly thereafter, Bert retired, and I have no idea if that had anything to do with our meeting or the ability of, or inability of, classical petrophysics to deal with something like this, but it was a great lesson because the well had a few feet of 9% porosity rock. And what's clear is that it was in a karst system, and that the karst system is connecting up to a larger tank not represented on the well log. And so it's very difficult to petrophysically evaluate reservoirs in karst systems. And so this is something that explorers for the Arbuckle and Berger Knox, it's a challenge, and recognizing wells that have potential that have not been properly completed is an opportunity. This schematic by Bob Laux, I think, is going to help elaborate some of these concepts. What we see here is a karst surface, and this could easily be the Knox unconformity or the Sauk-Tippecanoe surface. And you can see that there are some big caverns here with vertical shafts, and a vertical well could easily miss all of that and have virtually no porosity. Another vertical well could have very, very low porosity, less than 2 to 4%, just like the well in Wilburton, and maybe have a streak of 5, 10 feet or thereabouts of 9 or 12% porosity. But you can see that little bit of pH could be connected to an incredible tank with huge amounts of lateral permeability. And of course today, what is important to consider is the possibility of drilling a lateral well to intersect multiple tank, fracture, vertical shaft, other fractures, and to really very, very effectively drain by tapping into the system a very heterogeneous reservoir. One of the key things to look at are FMIs and cores in low porosity rock, and when it can be confirmed that there is in fact a karst system active in the area, that can validate the model that I just showed you, and I think can be a very powerful tool to encourage explorers to, when they see that there's karst in either of these systems, to consider the importance of going laterally, because one well can intersect tight rock in such a system but still be connected up to larger systems. And a great example of reservoir variability is in a 50 million barrel field on the Ozona platform, Todd Field, and there's 40 wells, and once again the straight average would suggest that it's about 1.25 million barrels of oil per well. But the reality is you don't get average wells in a field like this. What you get are a few very good wells and a lot of not so good wells, and the sequence of which well comes first can have a very big impact on the development history of a field, or potentially the possibility of overlooking a field. If a very poor well is drilled on the crust of a structure and doesn't make good production, it's very possible that that can be overlooked. And if a great well is drilled on the crest of the structure, the field is developed. But if a not so good well, there may be some potential there. And in the case of Todd Field, the crest of the structure is about 300 feet of simple closure, and you can see there's a couple wells over 1 million barrels, and there are quite a few wells in between that are less than 1 million barrels. And the best well in the field is 15 million barrels, and it's not on the crest of the structure, it's on the flank of the structure. One of the tools that is potentially useful, and I hope that will have a lot of promise for the future, is the ability to see some of the karst fabrics with ever higher quality seismic data. And a great example is some work with high frequency data, seismic data, done at the surface in quarries in central Texas by Bob Laux. And they made, here's about 100 read the scale. This is about 1,000 feet in here. So they have maybe about 2 miles of intersecting lines on the surface, and this is a quarry pit face. And so here is the vertical profile of the quarry. You can see the paleocavern fill and a variety of blocks into the collapse. And by making a pseudo 3D, they were able to determine that there are non-karstified fabrics and that there are very chaotic blocks with brecciated paleocave collapse. And using these fabrics, they can make time slices, and there's a very pronounced northeast-southwest karst fabric. Usually karst has some kind of river drainage, and also frequently, if there's a fracture pattern, it will exploit that same fracture pattern. And the northeast-southwest pattern is a very prevalent fracture pattern in the Llano uplift, where the karstification occurred in this quarry. And another example is using actual seismic data in the Fort Worth Basin, where at this surface you can see some of the sinkholes that are evidenced. Here's the Arbuckle-Elmberger Knox unconformity, and you see the karst collapse and its effect on the overlying beds. So to wrap up, I'd like to just summarize some of the key strategies, lessons from the 100 years of Great American Carbonate Bank exploration, and some things that perhaps can be useful to explorers today going into the future. I think it's important to remember to focus on reservoirs and traps below the Sauk-Tippecanoe unconformity. I think that for the majority of the production, it occurs near this unconformity. The unconformity creates paleogeomorphic traps. It creates migration pathways, as we saw in Kansas. I think there are some examples where pays can occur away from this unconformity, and it's important to recognize when we're in those settings, like in the interdetrital zone of Michigan and some of the up-dip sand and dolomite reservoirs, and also in some of the down-dip reservoirs where there's a lot more limestone, and the dolomite, which is the main pay, can be removed or further down from the top of the unconformity. Those are the exceptions. The majority, the rule is in the Midcontinent where it's dolomite, is that the pays will be associated with the unconformity. In large structural blocks, such as occur in Oklahoma and in Midcontinent settings and along the Ouachita Maritime Thrust Belt, as we talked about, if they are encased in sandy sections or sections that have risky seal, it may be appropriate to go ahead and do fault trap analysis, because that may be the best way to predict viable traps in hydrocarbon fluid levels. Something that can be very helpful is to identify areas that have favorable fundamentals and, most importantly, free hydrocarbon shows, even if they are found great distances from existing production, just like Maben was 590 miles from Wilburton, the nearest significant production, at its time of discovery. I think that it's important to explore around wells that made some oil or gas. They may have failed to intersect permeable rock, but still be connected to unproduced oil and gas. An example of that would be Maben Field, where the Texaco well had very minimal decline over a long period, indicating that it was connected to a larger tank. And this is a comment about the pays below the Sauk-Tippecanoe unconformity. If you are in the interdetrital belt, such as occurs in Michigan, it may be very, very profitable to explore and deepen wells that may have only gotten to the very top of some of the pays, but that may have stacked pays. And I'd like to point out that I'm hopeful, and I look forward to continuing research on seismic, how it may help us better assess reservoir variability. And I think that as we have more and more high quality 3D data over some of these old mature zones, I'm hopeful that we'll be able to build the database of understanding if seismic can be an assist to us. And very importantly, when we're in a karst fabric, it may be the key to directionally drill so that we can intersect multiple karst zones and fracture zones. There's a great story about a field in the Edwards Arch of Texas, Snakebite Field, which was drilled in the late 80s. It was discovered with a vertical well. The team that discovered it saw that it had karst in an FMI log, and they realized that they did not have a commercial well in a vertical fashion, and they took the ingenuity to recognize that they were in a karst zone, and as we looked at in that example of the block diagram, they went directionally and they made what would have been a non-economic field with vertical wells into a 22 BCF field and an economic venture using directional wells. And it was the keen insight to recognize that they were in a karst system and that they needed to basically intersect more fractures. We looked at an interesting example in Ohio where there might be a Cambrian source rock subbasin beneath Camber-Ordovician carbonate reservoirs, which could potentially make for some interesting conventional traps. We talked a little bit about Canada and Greenland, and one of the things is that there is some production in Camber-Ordovician carbonate reservoirs in Canada in thrust belts. And we talked a little bit about the possibility of Cambrian shale in the Appalachian Fold Belt as a possible unconventional play. I'd like to show my final slide. I had a opportunity to visit with some colleagues about the oil and gas opportunities in Camber-Ordovician reservoirs, and one of the things we thought about was what are some of the workflows that a person can use if they're trying to assess the potential prospectivity of a prospect or of an area. What are the things that if you kind of quickly did them, you get a very good sense of the potential? And I subtitled this here, How to Make Money in the Great American Carbonate Bank. One of the first things I would do if coming into a new area is I would immediately look for a type log for the area, because I would like to see the carbonate bank, of course. I want the carbonate bank to be dolomite. Almost all of the production is out of dolomite and not limestone. So I'd want to see a lot of dolomite. I'd want to see where the dolomite was. I'd want to see good source rock. I'd want to see good seal in close proximity above the carbonate bank, so that if it were in fault traps, we would have good seal and source rock in fault juxtaposition or in or on the unconformable surface on top of the bank. I think the type log would tell an awful lot very quickly for someone coming into a new area. I think it would be very important to get a good source rock map, because the carbonate bank itself does not appear to be a source rock. There's been a lot of tests, and it is very low organic carbon, less than 1%, much less than 1% in the carbonates. It's a very oxygenating environment in subtidal, intertidal, supertidal zones, so there's very little organic matter documented thus far in the bank itself. So the source rock has to come from outside of the bank, and I would want to have a good source rock map so that we could prioritize where the peak maturity is and identify pathways to access the carbonate bank. Does the source rock impinge upon the unconformity, or is the source rock fault juxtaposed to traps, and how do the pathways work? Another thing I'd want to have, especially if there are sandstones that are potentially proximal to the reservoir, I'd want isopach maps of the Simpson, in the case of the Arkoma Basin, of the Spiro to Arbuckle top, Any potential thief zones I'd want to have isopachs of so that we could use these to prioritize based on seal relationships. If I was entering a new area, I'd want to find the scout tickets. I'd want to look for abandoned wells that might have hydrocarbon shows. We know that if there's live hydrocarbons, that's a very significant thing. I'd look for pressure data. And remember the example at Maben Field, very low pressure decline. And if they had low or no decline, I think that could indicate that there's a larger tank that needs to be revisited. I think it's important quickly to get to locate FMI imaging logs, core samples. Is there a karst system present in that area? And it almost always has, the Arbuckle, Elmberg, and Ox reservoirs almost always have karst associated with it. With that major unconformity, it's very likely that there is a karst system, and it's important to confirm that. And if it does occur in a particular exploration area, that can indicate that wells and prospects may be horizontal drilling candidates. And then one more thing I would like to have in any area that I would go exploring in, I would like to have a map of the unconformity at the top of the carbonates, because that is a likely migration path, a potential trap creator, and even thin zones at that unconformity, lag deposits of sand can connect up into other accumulations. So I think getting a good sense of the shape of that unconformity could be very, very helpful thing to do. And so with that, I would like to say that thank you to HGS for inviting me to give this talk, and to AAPG for allowing me to contribute to the Great American Carbonate Bank memoir as a tribute to the great James Lee Wilson. I'd like to thank my exploration partners who have enabled me to learn a lot of these lessons through experience, not just through a textbook, but in actually going out and drilling some wells and making some incredible surprises along the way. And I have to thank Jerry Friedman for introducing me to the Great American Carbonate Bank over 30 years ago as a professor. And on my wall at my office, Jet Ring keeps me inspired as to what my focus is every